Hey class, this is 8.6 in the book. This is on resonance structures. So let's take a look at this. Notice that I have ozone, which is literally O3, like this. There's the first oxygen, that's the second oxygen, that's the third oxygen. Let's do, just quick, I want to do a comparison to show you that there is, oh, son of a gun. I knew I was going to forget this. Best Lewis structure. So to show you that for the formal charge of ozone, I have my first oxygen here. That's oxygen 1, oxygen 2, and oxygen 3. And you guys know that valence electrons is 6, 6, and 6. And you know that because when you look at a periodic table and you count from left to right and cross and ignore the transition metals, we count 1, 2, 3, 4, 5, 6. Oxygen is in the sixth group from the left. So that's the valence electron. So I'm showing you a formal charge example. So I need a little bit more room here to show you the rest of this. So I take a look at breaking the bonds for assigned electrons. That says assigned. I couldn't shorten it or I'd be swearing on the board. So here I have for oxygen 1, I have 1, 2, 3, 4, 5, 6, 7. I have 7 here, which gives me a -1. For this oxygen, I have 1, 2, 3, 4, 5. I have 5, which gives me a +1, like that. And then for this one, I have 1, 2, 3, 4, 5, 6. So that's 6, and that gives me a 0. So no matter what I do here, I'm going to end up with a +1 and -1 because oxygen doesn't share the electrons evenly between the 3 oxygens when there's 3 of them in bonds. But notice what happens. I'm going to erase this. I'm going to erase the formal charge. I just wanted to show you what it's like to do a formal charge on a different, like on another example. So I erased that to show you that the formal charge shows us that this is probably the most stable structure we can come up with. The only other way we could do this would be to do it like this. And I know this looks basically exactly the same, just in like a mirror setting. So 1, 2, 3, 4, 5, 6, like that. So in this case here, I have each of the oxygens with an octet, which is like, that's one of my major ways to see if I got something that's going to work. Notice that up here I have the double bond on the right hand side, and down here I have it on the left hand side. These two are equal but opposite. They are resonance structures of each other. Okay, so what I'm going to do is I'm going to pull this off to the side and say, hey, these two here, figures, these two structures, just a little help here. That's all I need. There we go. Like this, they are the same but opposite. Okay. Ozone can exist as that one, or as the one up above, or the one down below, and either one doesn't make a difference. But they are different though, because one has the double bond on one side, and one has the double bond on the other side. Just to show you, like you can put the positive and the negative there to show the difference between. Resonance structures are the same, but like sometimes they're a mirror in image. Sometimes there's more than 2 resonance structures. This one has 2 resonance structures because there's only 2 possibilities to draw, to switch places with the single bond, the double bond. Other ones have more. So this is at odds with the true observed structure of ozone. So the true observed structure of ozone has both of these bonds the same length, which means these both of the bonds are exactly the same. So instead of having a double bond, that doesn't show up very well. Instead of having a double bond on this side and a single bond on that side, okay, or a double bond on that side and a single bond on that side, what they do is they say it's actually kind of the average of both. So there's like a single bond and a half bond, and a single bond and a half bond. So that there's basically 1.5 bonds on each side like this. Okay, 1.5 bonds on each side. Now, what we do is basically marry the two resonance structures together. So those two structures we put together, here's the one and there's the other. When we put them together, it gives us something that looks like this. The explanation is that when you mix the blue color and the yellow color and you get green total, like that's what we're doing with our resonance structures. So that resonance structures mean, I know this sounds confusing, but the ozone molecule exists kind of as both of the resonance structures. That's what it means. It means that the double bond is not on the left-hand side, it's not on the right-hand side. It's an average between the two. So that's what we focus on. So a resonance structure tells us, like, one resonance structure is only half of what the actual truth is for the ozone molecule. So I put this resonance structure with this resonance structure, and what I get then is a situation where I get like 1.5 bonds to each of the oxygens here and here. Okay, so like 1.5 bonds to each of the oxygens. That's what we got for resonance. Notice this one here is very similar. Here the double bond is the one that goes out to the right, and here it's the one that goes down to the bottom. Although they both have the same number of atoms and have the same charge, what happens is that these two bonds are single and double bonds, but they end up kind of averaging to 1.5. Sometimes we get the same thing. These structures here, when they write organic compounds quickly, at every corner is a carbon, and you can see the single and the double bond. There's a carbon there, just like you see up here. These two are exactly the same. So they have one where the double bond's on the top and bottom left and bottom right, like this, on the top, bottom left, bottom right. And then they have them where they switch places where it's on the bottom, top right, top left. But in total, it's 1.5 bonds between each carbon, so that we can have six carbons, and instead of 6 single bonds or 6 double bonds, we have basically like 1.5 bond between each one of them. And that's how that works. So I know that sounds kind of like magic or something, but that's the idea, is that every time we take a list, this right here, by the way, is called benzene, and benzene looks like this, where between each carbon is a bond and a half, and you're going to see that a lot for resonance structures. Okay, I'm going to stop there because exceptions to the octet rule is 8.7, which is coming up.